Function Block Diagram Programming, FBD, is a graphical programming language similar to LAD programming. And like a LAD program, an FBD program or program block is composed of numbered networks. As shown in the accompanying graphic, an FBD program is made up of instructions that use the same types of operands and tags as a LAD network. As with a LAD program, in Step 7 TIA Portal, an absolute operand is preceded by %, a global PLC tag is enclosed in quotation marks, and a local tag, which is a tag defined in a program block for use only by that program block, is preceded by the £. Step 7 TIA Portal also provides the option to display absolute operands and tags at the same time as shown in the accompanying graphic. Because the FBD programming language includes many instructions, Step 7 groups instructions into a number of basic and extended instruction categories. These instructions provide FBD with similar capabilities to those of LAD programs, and in some cases the instructions look the same. However, there are some important differences. Some of those differences are shown in this lesson, which provides examples of instructions in the bit logic category. As the PLC scans the user program from top to bottom in a program block, each network is scanned from left to right. Just as with the LAD program, the solution for a configuration of instructions is called the result of logic operation, RLO. Using the simple network shown in the accompanying graphic as an example, the two instructions on the left are solved first. The logical solutions to these instructions are provided as inputs to the next instruction. The logical solution to this instruction is provided to the final instruction, which in this example assigns the result to an output status bit in the process image. As shown in the accompanying graphic, the assign instruction is the FBD equivalent to the LAD output coil instruction, both of which store the logical result of the network in a memory location specified by the operand. When the RLO to the assign instruction is 1, the instruction sets the operand to 1. When the RLO to the assign instruction is 0, the instruction resets the operand to 0. Some FBD bit logic instructions are derived from Boolean logic. One of the most common of these instructions is the AND instruction. The accompanying graphic shows an AND instruction with 2 inputs, but an AND instruction can have 3 or more inputs. The operand associated with each instruction input identifies the memory location where a 1 or 0 is stored. In this example, only I operands are used. However, Q and M operands can also be used. As the associated truth table shows, the result of the AND operation is 1 when both of the inputs to the instruction are 1s. When there are more than 2 inputs to the AND instruction, all inputs must be 1s for the result to be 1. The AND instruction can be combined with other instructions to form a network. In the accompanying graphic, the AND instruction is combined with an assign instruction that controls the machine 2 process image status bit. In this example, machine 2 is 1 when switch 1 and switch 2 are both 1s. The OR instruction is another FBD bit logic instruction. The accompanying graphic shows an OR instruction with 2 inputs, but an OR instruction can have 3 or more inputs. In this example, the instruction inputs are I operands. However, Q and M operands could have been used. As the truth table shows, the result of the OR instruction is 1 when 1 or more of the inputs to the instruction are 1s. The OR instruction can be combined with other instructions to form a network. In the accompanying graphic, the OR instruction is combined with an assign instruction that controls the machine 2 process image status bit. In this example, machine 2 is 1 when either switch 1 or switch 2 or both are 1s. The accompanying graphic shows an FBD exclusive OR instruction with 2 inputs, but an exclusive OR instruction can have 3 or more inputs. In this example, the instruction inputs are I operands. However, Q and M operands can also be used. As the truth table shows, the result of the exclusive OR instruction is 1 when one of the inputs to the instruction is a 1, but not when both are 1s. This rule must be expanded to take into consideration exclusive OR instructions with more than 2 inputs. The broader rule is that when an odd number of instruction inputs are 1s, the result is a 1. But when an even number of inputs are 1s, or when all inputs are 0, the result is 0. FPD instructions are often combined to form networks that perform more complex functions. For example, the accompanying graphic shows a network of 5-bit logic instructions. By analyzing the truth table shown, you can determine the status of output machine 4 for any combination of operand statuses. Inversion, also called negation, means to change a 1 to a 0 or vice versa. When applied to FPD programming, an invert instruction is represented by a small circle adjacent to another FPD instruction. The accompanying graphic shows an example of an invert instruction on one input of an AND instruction, but the invert instruction can be used with other FPD instructions as well. As the associated truth table shows, the result of this logic combination is 1 only when switch 1 is 0 and switch 2 is 1. Without the invert instruction, the result is 1 only when both inputs are 1s. Another type of inversion available for S7-1200 and S7-1500 PLCs is the negate assign instruction. The negate assign instruction inverts the RLO of a network. Therefore, if the RLO of the network is a 1 without the negate assign instruction, the RLO is a 0 with the instruction and vice versa. For example, the accompanying graphic shows a network with an OR instruction connected to a negate assign instruction. As the associated truth table shows, the result of this network is a 1 only when both of the inputs to the instruction are 0s. With an assign instruction instead of a negate assign instruction, the result is a 0 only when both inputs to the instruction are 0s. There are a variety of FPD instructions that set and/or reset bits. For example, the accompanying graphic shows a set instruction. When the RLO to the left of the set instruction is 1, the instruction sets the specified bit to 1. In this example, when level 1 and valve 1 are both 1s, the set instruction sets pump 1 to 1. Output pump 1 remains a 1 even after the result of the AND instruction returns to 0. The accompanying graphic also shows a reset instruction. When the RLO to the left of the reset instruction is 1, the instruction resets the specified bit to 0. In this example, when either level 2 or pump 1 or both are 1s, the reset instruction resets pump 1 to 0. Output pump 1 remains a 0 even after the result of the OR instruction returns to 0. The accompanying graphic shows 2 other instructions as set and reset bits. The top network includes a set-reset flip-flop, and the bottom network includes a reset-set flip-flop. Both networks perform a similar function. When there is a 1 at the set S input, the output Q and the memory bit specified by the operand at the top of the instruction are both set to 1. They remain a 1 even after the set input goes to 0 until there's a 1 at the reset R input. There is one important difference between these instructions. For the set-reset flip-flop, the reset input is dominant. For the reset-set flip-flop, the set input is dominant. If there's a 1 at both the set and reset inputs, the dominant input controls the result. The instructions shown in this lesson are only a few of the many types of instructions that can be included in a Siemens PLC FPD program. An FPD program in a Siemens PLC can include a variety of basic and extended instructions. As you have seen, some of the FPD instructions are different from corresponding LAD instructions but the instruction categories and overall capabilities of FBD and LAD are very similar.